Hey guys, this lab is about interference and diffraction. So laboratory 5. Mm, so initial plan was this. We sent students with slides for diffraction and interference in their lab kit. I just happened to realize it yesterday that I forgot to purchase a laser and send that along in the kit. So since they don't have a laser, which means I think those slides are going to be useless now. So we ended up making this simulation lab here for lab 5. Okay, so lab 5 here, resources and equipment list are here. Student would need their ruler. Number 2, just the website. We are going to use a FET Colorado simulation, and another one is from GeoGebra. Part 1, experiment about single slit diffraction and double slit interference. This is just to show, a student like where the laser would be, where the slit plate, and where the screen is. So if you student go to this website, they will see, before I click on that, let me tell you guys a little bit. So from this website, students are supposed to choose this diffraction from the given options. There are several other options, and then they should, once they are there, they should set the wavelength to 700 nanometer. And once they are there, they are going to observe the diffraction simulation. So if I go here, so you see there are several options. So for this part of the lab, we'll use diffraction, but students will also need to use slit for some other part of the lab today, okay? So diffraction, if I click on diffraction here, it's gonna look like this. Here is a laser, there is a slit, aperture, small little hole here, circular hole, and there is a screen. Students are asked to put this to 700, which is like red light, right? Somewhere, like this. Oops. So that's the 700 nanometer wavelength, and then once they have there, they can play with this little bit here, and then just if you shoot the laser, then you see this, there is this nice pattern. We see there is a high intensity in the middle, and then this has a lesser intensity, and this intensity of the light keeps decreasing, right, as we go away from the distance. So if we are to really have this graph, then this is going to be like the central maxima, right? When we have a diffraction pattern, central maxima. And then if we were to measure the distance, we would measure from here to the brightest part here, like this here, and then go to, so this black part would correspond to m equal to 1, right? Black, this fringe here, this would be m equal to 2, this would be m equal to 3, and so on. In this one, students are not going to do any measurement. They are asked to just vary this diameter. Maybe they could make minimum and then to maximum, right? So as you make the diameter maximum, we see the distance from the central maxima to the to the dark fringes, it decreases, right? So, but then if we make the smallest diameter, then the distance from the central, maxima to this fringe increases, right? So that's the observation. So that's just qualitative for a student to observe. The other part, and this one also shows here, like this is just a sample diffraction pattern for single slit. This is the same as the one we had over there, but this is just taken in a different way, right? This is just a slice of the. If we were to make a like slice like we had, if we were to like actually just make that graph we saw earlier, the pattern directly in between, if we slice it in the middle, and then if we look at from the slice part, then this is what it would look like, right? Highest intensity here, and the distance from this maxima to this dark spot, that is this dark fringe, this point is M1, right? So that distance corresponds to dm1, okay? Bright from central maxima to dark fringe. First dark fringe is m equal to 1, okay? So, and then students answer question here. Next part of the lab, this is also about the single slit diffraction. Here actually student would need to do some calculation. They are going to basically what they are going to do is they are going to make use of this angle here, this equation here, b sine theta m equal to m lambda. For a very small angular position theta m, we can write sine theta as equal to tan theta, and that it really turns out to be dm divided by lambda. And then after substitution they should really use not this equation but this one. This is right, b equal to m lambda l divided by dm. So what they are going to do here is, make a measurement of this dm, that's the angular position, from the central maxima, okay? So m, m equal to 1, 2, 3, so on. And then they will have some wavelength of light L, and wavelength would be constant for the given experiment, okay, simulation. So let's look at quickly. So this is what we have here. As you, okay. So this is what we have here. There are parameters here that the student can change. This D is same as the L in our equation, okay? So this is something you may have to explain to a student. I naught is intensity. They should not do anything here. B is given here, 10.1. Lambda is 2. So they can just leave these values as it is. What they should do is, this is the intensity, right? So in the fit simulation we saw there was a highest intensity in the middle, so this peak corresponds to that part. I mean, it's not the same simulation, but if we were to draw a graph for that intensity, it will be something like this: intensity versus angular position on the x-axis. So here what students should be doing is this, they should be measuring the distance from central maxima, right, this peak which is here at 0, to the first minima, right? So this is the minima, which is the value of this curve, right? So minima, so they can measure this distance, and that would be their dm1 corresponding to m equal to 1. And then they should also, measure the distance of this m equal to 2, which should then this distance here, okay? So here, look at this, right? So this is what we have right now, but if they end up changing some of the value of b to some other value, I mean, oops, not that, right? Something like this, right? Like, so then it's kind of harder to say what value we have here. So if they do something like that, what they could really do is just use their ruler. They can measure distance from here to this 1, right? And that distance should be, correspond to some centimeter, maybe 0.5 centimeter in their ruler scale. And then they can, measure the distance of this minima from here to there and use the conversion factor, right? So let's say 1 centimeter, I mean, this 1 unit correspond to half centimeter, right? Then 1 centimeter would be just two units on x-axis. And then whatever the value they measure here, then they can just multiply that with 2 to just get the actual number, okay? So that's one way. Another way is probably, this is something I didn't look at earlier, but I mean, maybe we could just ask them to put this b equal to 5, or maybe, let's say, yeah, b equal to 5, and then that way they can just, I think, oh, maybe this is much easier or simpler. If they put b equal to 5 value, then, everything is just right there, right? Like 2, 4, 6, and so on. But then if they make other value, other value, then it's kind of different value, right? It's like, I mean, we have to use the conversion factor using the ruler, okay? So here student will have a value for m equal to 1, m equal to 2, I mean, dm, right, value of the distance from central maxima to the minima, right, this value, so they should find this distance for several value of m, okay? Once they have that, then they can compare measure value of that b, right? no, they will have this value measured from the simulation dm. Lambda also they have it in simulation, L also they have in simulation, M is something they should take consider M equal to 1, 2, 3 and so on. And they can calculate this B. After they calculate this B, they can compare this value with the value of B that is given in the value of B that's given in the simulation. So this value here, okay. All right. After that, repeat using a different single slit aperture width. So there is where they can change this value of B if it's really easier, right? If they do double the value from what they had before, it would be much easier to see the pattern in the data. Okay, so I did a simulation and I looked at, and it looks like this. This won't be in the student's copy. This is just for you to just get an idea. So it kind of matches with less than 3% error. So okay, so for next part of the lab, students will use the slit part from the simulation, okay. And then for this part here is again this is about the Young's double slit interference experiment. So here is a sample slit plate here. This distance between the slit plate to the screen is L, right? This is the screen, and D for M equal to 3. So this is the most important thing here. When we make a measurement of this distance in interference pattern, we make a measurement from the maxima, right? Really, I mean, they have an equal width really. So this one of these central maxima to the bright fringes, not the dark fringes. Okay, so that's the important thing. I think we should emphasize that to student, bright fringes. Okay, and then they will use the same equation like we had before. Again, they should do the, of course they won't have a sine theta m, so they should just really use the equation we had up in the at the beginning, and then here they can just measure the value of m, I mean label m lambda wavelength, L is in nanometer, dm is that distance, angular position, and determine value of a using measured value of this. They can calculate a, and then theoretical value. Let's say if theoretical value is the value we are given in the simulation, which is this value, and then if you look at the percentage difference, it is kind of high. So let me go back to the simulation. So here, did I turn off the simulation we had before? I guess I did. Okay, this one I can turn this guy off. Okay, so here for this part we have to go to slits. Okay, so once we get there, student can once they get there, they can familiarize themselves with the feature. The important thing we are going to use here is this. From here, first of all, we will change this one slit to two slit. Okay, and from the source, instead of this water, this is for sound wave, we will use the light source here, which looks like this, like laser light here. And then this is also check this screen and then intensity. Okay, so that way it would be easy to look at the data, easy for reading data. And then here is a tape measure that a student can use to make a measurement. So light, oh, this is giving me headache again, like migraine headache. So there are two ways to, I think, really determine the frequency. I mean, it gives symptoms of, excuse me, frequency, but really students should use they will need the wavelength. Okay, so one way to do is kind of look at the first part of diffraction where it gives us the value in the nanometer, right, like wavelength. Or another way to is measure this, to use this tape measure to measure the wavelength. Okay, so let's look at it here quickly. If we turn this on, we see the red light, right? Oh, this is again in one slit. I guess this didn't. Okay, we need this to be in two slit. Okay, so we have a two slit here. The distance from here. So let's see. See, look at that pattern. Oh, one more thing. So if they put this slit separation far away, we get to see. Then we'll see the multiple value of m. Okay, or multiple fringes. Okay, so let's see. Yes. Okay, do you see now it has increased, right? So student would need to measure, right? So this is this from here to here is this distance is the L, right? So if you use this guy here all the way to over here, that's the screen distance of the screen. That's gonna be the L, right? Distance, okay. Um, and then they have to use from distance from the oops. How do I make this go away? Okay, I don't need to use that. I'm gonna just leave it there. So they can use use this as like m minimum maxima right here, and then since this is the interference pattern, they have to measure the distance from this peak to the brightness, right? So this next peak here. Okay, so peak to peak, and then so this would be m equal to 1, this would be m equal to 2, and so on. Okay. For a wavelength measurement, they can just if they just pause this, and then they can just make a measurement of the wave, right? So wavelength is really the distance from this center of this wave to the center of this, right? Really the distance traveled by the wave before it starts to repeat, right? So from here to here, from here again it starts to repeat, right? So that can also give them the wavelength, right? So maybe somewhere like in between here, and then take this guy, put there at the center. So that will also give like wavelength, right? Lambda value. Or they can just kind of look at carefully this color code here and go to the like the diffraction part, and then look at just the nanometer value, like wavelength value there. Okay, that's also fine. So after so where is my okay. After it is done, after they do this, they are going to get the value, right? So m wavelength, lambda, right, LDM, and then just compare those value here. It does have a high percentage error, so probably that's something they will also find that. Part 2 is a research question. What questions do you or your group have about interference and diffraction? They may ask you, since it may not look like direct to them, one of the way to do, I think one of the questions, right, really easy question would be just change the color, right? Like if you have a different color, it means it will have a different wavelength, and then just maybe just do the same thing here, like the double slit experiment, or even for the other part, right, where they did the single slit experiment, right, in the simulation. So one of those would be, they should be able to do one of those, or they can come up with their own question. Post-lab discussion question: how can you quickly tell and easily tell the difference between diffraction and interference pattern? Diffraction has a larger central peak. We also saw that interference fringes are all the same width. When measuring fringes on a diffraction pattern, do you measure to the maxima or the minima? Of course, we measure it to the minima, right? Darkest spot. And when measuring fringes on an interference pattern, do you measure to the maxima or the minima? We measure it to the maximum brightest spot. Okay, so that's about it for this lab. Sorry, especially to Jeff. It took me a whole day to really work on this, make this, because I was expecting to, have the lab that was already ready, and that was for the actual lab, like using the slides and so on. But it's my fault. I forgot to send the students a laser, so we had to write this whole thing. All right, thank you guys for watching.